Here's a question that I asked you to work on based on Newton's third law. You'll remember that Newton's third law, what sounds like sometimes the easiest of the three laws, but what amounts to sometimes the hardest of the three laws, says if object A applies a force on object B, then object B applies an equal and opposite force on object A. This is just a question that mathematically reflects what we've learned with that law. Okay, that equal and opposite force thing. It says a 15-kilogram toddler gets in an argument with a 20-kilogram toddler and pushes him. The 20-kilogram toddler accelerates at 1.5 meters per second squared. 15-kilogram toddler pushes for 0.55 seconds. What's the final speed of the 15-kilogram toddler? We're going to call the 15-kilogram toddler object A, and we're going to call the 20-kilogram toddler object B. So we're now treating these little kids like objects. We're going to say that the force of A on B, the magnitude of it, sorry, the force, not the magnitude, the force of A acting on B is going to be equal to the force of B acting on A, but opposite in direction, equal and opposite. Now we're going to say FAB is m times a. The mass of object B times the acceleration of object B. It's equal to negative mass of object A times the acceleration of object A. What are we going to do here? We got everything except the acceleration of object B here. The acceleration of object A. So let's plug in our numbers and find that acceleration. Okay, let's say that mass B, 20 times the acceleration of object B is 1.5 equals negative 15 times the acceleration of object A. This is not what we're looking for, but that's okay. Okay, we've talked about this before, right? We don't have to necessarily get what we're looking for right away. If we're doing something that's valid, if we're doing something that's not wrong, it doesn't have to right away lead to the final answer. Okay, that's the case here. 20 times 1.5 is 30. 30 divided by 15 is 2. So we're going to say the acceleration of object A is negative 2.0 meters per second squared. That's not a big surprise, right? Object A is lighter than object B. Object A should therefore have a bigger acceleration than object B. And it does. But the only problem is it's not my answer, because I'm looking for the final speed. What am I going to do now, though? What am I going to do now to find the final speed of object A, the 15-kilogram toddler? This is a group B problem, right? This is a last unit problem, a problem that you guys worked on lots and lots and lots in the last unit, and you nailed it in the last unit. Okay, we have the acceleration of object A. We have the time of contact. We have the initial speed is 0. We're looking for the final speed. Let's use one of my group B equations and say A is equal to delta V over delta T. Rearrange it. Delta V is equal to A times delta T. Negative 2.0 meters per second squared times a time of 0.55 seconds. That's going to give me 1.1 meters per second. If the initial, negative 1.1 meters per second. If the initial speed is 0 and the change in velocity is negative 1.1, then my final velocity will be negative 1.1. Why negative? Well, because the other guy went forward. This guy's got to go backward, right? If the one guy had a positive velocity, then the other guy has to have a negative velocity, right? I'm going to do another one now. This one's harder. This one is not the same thing as we just did, but it is tied to Newton's third law, but also to Newton's second law. Here's the deal. We've got a force applied to the right of 50 newtons caused by whatever, doesn't matter what's pulling it, it's 50 newtons. We have a force of friction to the left acting on the 10 kilogram object of 20 newtons, but a force of friction acting to the left on the other object of 25 newtons. And then there's a rope or some kind of connecting cable that joins the two masses together. We want to find two things. The acceleration of the system, which we know how to do that very well right now. Okay, I could set you free on question A by yourselves. You could do it by yourselves. I'm confident of that. Question B, though, that's a bit tougher. What's the tension in the rope joining the two boxes? In other words, With how much force does object 1 pull on object 2 with? Or you could think of it the other way, with how much force does object 2 pull on object 1 with? Sometimes we like to call these external forces because they're acting on the system externally, right, outside the system. But we would call this one an internal force because it's acting within the system. Does that make sense? So it's like you got two little kids in a wagon. The external forces on the wagon would be me pulling the wagon, would be friction acting on the wagon, maybe some air resistance acting on the wagon. The internal force would be the two kids pushing each other inside the wagon. They don't affect the motion of the system, but there's still forces acting inside the system. Okay, question A involves just external forces, and that's all we've dealt with so far, so we're good with that. Question B involves finding that internal force, which we've never done. I'm going to go through question A with you, even though you can do it yourself, and then I'll go through question B with you and guide you through the steps in solving this new kind of problem. All right, so question A says, find the acceleration of the system. Here's what I want you to do. Treat this as if there's no rope between it. Treat it as if there's a box. Treat it as if there's a box that has a mass of 25 kilograms. Maybe it's a semi-truck, and you got a whole bunch of objects in the back of this semi-truck, separate objects. But when we're analyzing the motion of the semi-truck, we're just going to treat the masses all as one, right? You got this big object at the front of the trailer, this big object at the back of the trailer. Who really cares when we're analyzing the motion of the truck? We just consider it to be one big trailer. That's what we're going to do here for question A, and you know how to do this. We know that the net force is equal to the sum of the forces. That's going to be FF1 plus FF2. Right, the force of friction on the first one plus the force of friction on the second one. Friction's acting on both, so it's important to include both of those forces, but I don't need to include that internal force. The two little kids pushing each other in the back of the wagon is irrelevant for the motion of the wagon. The internal forces don't care here, don't matter here. We're going to add the applied force to that. Now, since I want to find the acceleration, I'm going to set F net also equal to m times a. So I'm going to say, once again, FF1 plus FF2 plus the applied force. What are we going to use for the mass here? What do you think? 10, 15, 25? What are we going to use here? Taylor? Good, 25. If you're talking about that semi-truck, it's not the mass of the trailer that matters. It's not the mass of object 1 inside the trailer that matters. It's the mass of everything that's inside that trailer. It's the total mass. If you're talking about the wagon again with the two kids on the back, we're including the mass of both kids, not just one of them, right? Both kids and the wagon. So the total mass here would be 25 kilograms. FF1 is negative 20 because it's to the left. FF2 is negative 25 because it's to the left. And FA is positive 50 because it's to the right. So I end up getting 25 times A equals positive 5. A ends up being equal to 5 divided by 25. I think that's 0.2, 0.20 meters per second squared. So that's not really anything new, is it? Except for recognizing that that 10 and the 15, for purposes of question A, are really just one object. All right, now we want to find the force of tension in the rope joining the two boxes. In other words, we want to find an internal force. That's new. Although you're going to see the technique that we use to solve this is much like the technique that we've already used to solve question A. But there's a couple little things that you got to do. Here's what I want you to do. Every time you want to find an internal force. Okay, external forces, hey, we deal with it the same way as we did question A, same way as we dealt with the questions that we've already solved in class. You want to find an internal force, you got to pick an object. Pick one object. Either the 10 or the 15, right? You got the wagon with the two little kids inside. pick either the kid in the front of the wagon or the kid in the back of the wagon. Analyze one of them. You want to find an internal force, analyze one of the objects. Now, it doesn't really matter which one you pick. One is usually a little bit easier than the other, but both of them should give you the same answer. Pick one object. I'm going to pick the 10 kilogram object. Okay. And I'm going to draw a free body diagram for the 10 kilogram object. But only the 10 kilogram object. Right? The 15 kilogram object it's still there, but I'm analyzing inside the system now. So I'm picking an object. That 10 kilogram object has a 20 Newton force of friction acting on it. I'm not going to draw the 50 because it's not acting directly on the 10. It's acting directly on the 15. I'm not going to draw the 25 because it's acting on the 15 as well. Now I'm drawing only the forces acting on the 10. Are there any more forces acting on the 10, by the way? Besides gravity and the normal force that cancel? The 10 kilogram object isn't going to go anywhere if it's not being pulled. Right? I pull on this wagon with 50 newtons. Okay, the 10 kilogram object has to be pulled. Otherwise, it's staying where it is. If there's only one force acting to the left, in fact, it's going to go to the left, right? There's got to be a force acting to the right on it. We're going to say that force acting to the right is the force of object 2 acting on object 1. The 15 kilogram object is pulling on the 10 kilogram object to the right. I don't know what that force is, but that's what I'm trying to find, right? I'm looking for the force of tension in the rope joining the two. What is it that's pulling them? That's joining the two? It's the rope. So the force that I'm looking for is that force of tension, that force of the rope, the force of 2 acting on 1. And we know what to do here now. F net is equal to the sum of the forces. FF plus F21. F net is equal to M times A. Remember, I'm analyzing only one object now, not the system. What mass do I use? 10, 15, or 25? If I'm analyzing only the kid at the back of the wagon, then I have to use the mass of the kid at the back of the wagon, not the mass of the kid at the front. I'm analyzing the kid at the back. The mass of the object 1 is 10 kilograms. We already know the acceleration. Here's the key. We know the acceleration. If the system accelerates at 0.2 meters per second squared, then each of the objects within the system accelerates at that rate. All right, what's the force of friction here? We're going to make it negative 20, and we're going to solve for F21 here. 10 times 0.2 is 2. And we're going to take that 20 over by adding. We're going to get a value of F21 of 22 newtons. So how hard does this rope have to pull on object number 1? How hard does object 2 have to pull on object number 1? 22 newtons. The internal force of 22 newtons. Now, what if I had picked object 2 to analyze, the 15 kilogram object to analyze, the kid at the front of the wagon? The pallet at the front of the truck to analyze. Let's try it. Let's give it a whirl here and see what happens. Okay, if we're analyzing the second object, its mass, I think it was 15, wasn't it? 15 kilograms. Yep. There's a force of friction acting backwards on it. It was 25 newtons. There was an applied force to the right acting on it of 50 newtons. Anything else besides gravity and the normal force? Yep. Yeah, the rope acting on it, right? How is the rope acting on it? Okay, the 15 is pulling on the 10, right? The 10 isn't pulling on the 15, is it? wait a second, if object A applies a force on object B applies an equal and opposite force on object A. Here's the tie into Newton's third law, right? That's why it doesn't matter which object we analyze, okay? It seems more logical that the 10 is pulled by the 15, but the 15 is also pulled back with the same force as the 10 is pulled. Well, I'll call that F1, 2, the force of object 1 on object 2. We're going to say the net force is equal to the sum of the forces. We're going to say MA is equal to the sum of the forces. The mass this time I'm going to use is 15. The acceleration is still 0.2 because, again, the system accelerates at that rate. Everything within the system accelerates at that rate. F12 is, that's what we're looking for here. FF is negative 25, and FA is positive 50. 15 times 0.2 would be 3. F12 plus 25. Take this over by subtracting, and F12 equals negative 22. Is it a coincidence that F21, the first way I found it was positive 22, and the second one, F12, is negative 22? If object of A applies a force on object B applies an equal and opposite force on object A. You got to do it both ways? No, of course not. You see a question like this on the test, do it one way or the other. Having said that, if you got extra time, you try it the other way. It's a good check. If you get the same answer both ways, you're right. Like 100%, you're right. If you get a different answer when you're solving it, one object or the other, then you're wrong. Try again. So what are the steps in finding an internal force? We know how to do the external force, right? So do it. Get the external force. Get the acceleration from analyzing the external forces. And then pick an object. Doesn't matter which object you pick. Pick one of them. And then solve for the internal force, analyzing only that one object. It's as simple as that. It really is. Okay? Get the acceleration by analyzing the external forces, which is what we've been doing up until today. But now, to solve for the internal force, you got to pick one object, go with the same process, just solve for the internal force acting on that one object. Let's try this one individually at your desks. Okay, now, I haven't broken this down into two steps. I just said find the force of tension in the rope joining the two boxes. Is that an external force or an internal force? External force or internal force? Yep. Yeah, that's going to be an internal force. That's that force right there. And what do you got to do? Okay, we draw that little line down the middle, get the acceleration using the external forces, which is what we've been doing for days now, and then analyze one object over here to solve for that internal force. All right, let's have a look at this one now. Remember, when you see one of these problems where we want to find an internal force, and that's really what we want to find here, right, is the force of tension between the two of them, an internal force, then we have to first find the acceleration in the same way as we found it in all the other questions that we've done, and that is analyze one object, the entire system. Okay, this system has a mass of 30 kilograms. Pretend it's one object, right? It's a semi-truck with a 12-kilogram crate and an 8-kilogram crate in the back of it. The semi-truck has a mass of 20 kilograms. We'll say the net force is equal to the sum of the forces. We're going to say that's FF. We'll say FF1 plus FF2 plus the applied force here. M times A is also the net force. And we're going to say M is going to be 20 kilograms. Again, we're using the entire mass. We're analyzing the entire system. Okay, this is a question like 2 days ago you would have gotten, except that 2 days ago it wouldn't have been a 12 and an 8. It would have just been a single 20-kilogram object. It doesn't change that, right? Now that I have it separated. It doesn't change this part of it, at least. FF1, negative 18. FF2 is negative 12. FA is 45. Get 20 times A is equal to That's 15. On the right side, A is equal to 0.75. So the system, the back of the truck, the wagon with the two kids in the back, whatever it is, accelerates at 0.75 meters per second squared. And everything within that system accelerates at the same rate. When you're in your car and your car accelerates at 0.75, you accelerate at 0.75, and so does the person in the back seat accelerate at 0.75. All right, now to analyze the internal force, we've got to pick one object. Which one do you want to pick, the 12 or the 8? How many people pick the 12 to analyze? How many people pick the 8 to analyze? Okay, more the 12. Okay, I picked the 12 as well. Does anybody have a good reason for picking the 12? They both work. Is there a reason why the 12 kilogram object might be a little bit better diamond than the 8 kilogram object? Yeah, there's less forces. That doesn't really matter. If you draw the 8, it just means you have 3 forces acting on it instead of 2. It's a tiny bit more work. It's not harder. It's just a tiny bit more work. And hey, if you can save a little bit of work, save it, right? 12 kilogram object has a force of friction acting backwards of 18. And the only other force acting on it, besides the normal force and gravity that cancel, is going to be the force of tension in the rope. We're going to call it F21. We're going to say F net now is equal to FF plus F21. Only the force is acting on that one object. MA is equal to FF plus F21. Remember, right now, talking about that wagon and the kids again, we're analyzing one of the kids, not both of them. Okay, the kid at the back of the wagon. Okay, we're going to use the mass, therefore, of the kid at the back of the wagon or the box at the back of the truck. The acceleration is 0.75. We established that if the system accelerates at that rate, so does every object within it. FF is negative 18 plus F21. 9 equals negative 18 plus F21. And F21 equals 27, I think. How many people got that? Good. If we had some time and we wanted to double check our work, then we might want to choose to analyze the 8 kilogram object, okay? If this is a test question, okay, I'm not going to go back right now and analyze the 8 kilogram object. I'm going to go back and do the rest of the test. But if I have 15 minutes left or 20 minutes left at the end of the test, that's when I might go back and say, hey, look, I got a little bit of time. Maybe I'll just try analyzing the 8 kilogram object and see what I get. If I get the same answer, except negative 27, when analyzing the 8, then I'm right. Okay, if I get a different answer, then I've made a mistake. How does this tie into Newton's third law again? Well, not a whole lot, but it does tie together Newton's second law and Newton's third law a little bit. And that we recognize that the 8 pulls on the 12 with the same force but opposite direction as the 12 pulls on the 8. We just went over a question this morning in Physics 30 on an assignment that half the class got right and half the class got wrong. 50%. And I said to them, you know what? My Physics 20s would nail that question. It was a question about electric force. You guys know nothing about electric force, but you could still nail that question. This has got some charge on it. This has got a lot more charge on it. The question was basically, how does the force of object 1 compare to the force on object 2? Okay. What's the answer? It doesn't matter what kind of force it is, electric force, gravity force, whatever force it is, if object A applies a force on object B applies an equal and opposite force on object A. So despite the fact that this has a lot more electric charge, the force on it ends up being exactly the same, equal and opposite to the other force. Okay. rears its head in physics 30 a lot, just as it does in physics 20, not with the same types of forces that we're talking about in physics 20, but it's still the same idea, right? Object A applies a force on B, B applies an equal and opposite force on A. All right, I'm going to give you a few minutes to work on a few questions here now on page 168. The questions I want you to work on are questions 1 through 8 on 168.